Hi viewers, welcome to my class on mechanics of materials. In this class, I'll introduce the concept of lateral strain and Poisson's ratio. We have already studied linear strain or longitudinal strain. When a material is loaded, the strain induced in the direction of load is linear or longitudinal strain. So that is deformation in the direction of the load divided by initial length. So change in length in this bar, the linear strain is delta L by L. Delta L, initially the length is L, and after the load is applied, the length increases by delta L. So the linear strain induced is delta L by L. So change in length divided by original length. That is a linear strain or a longitudinal strain in the direction of the load. So as the length is increasing, there will be a change in the lateral dimension, that is a diameter. In this case, the diameter of the bar decreases. So initial diameter is D, and the diameter finally of applying this tensile load, the diameter decreases, and final diameter is D minus delta D. If it is a compressive load, the length will decrease and diameter will increase. So the change in the lateral dimension divided by original lateral dimension is known as lateral strain. So lateral strain is change in lateral dimension divided by original lateral dimension. See, here the lateral dimension is diameter. So change in diameter divided by initial diameter, that will give the lateral strain. If you are taking the sign into consideration, then you need to go for final diameter minus initial diameter divided by initial diameter. In that case, you will get a tensile load giving a negative strain and a compressive load giving a positive strain in the lateral dimension. Because tensile load will decrease the diameter, you will get a negative lateral strain, and compressive load will increase the diameter and you will get a positive strain. So most of the cases you can take a numerical value of lateral strain, that is without considering the sign convention. Now if a cross section is rectangular, there are two lateral dimensions, width and thickness. So when you apply the axial load, the length will change, and delta L by L give the linear strain or longitudinal strain. But lateral dimensions also simultaneously changes, and width here it is decreasing and thickness is also decreasing because it's a axial pull. So the change in width divided by original width, initial width, delta W divided by W, that will give the lateral strain. And similarly delta T by T also gives the lateral strain. So the lateral strain, both the lateral dimensions will be same. So delta W by W is going to be equal to delta T by T. So one of the lateral strain, if you calculate, the other lateral strain is going to be same. So if you get delta W by W, that is known, you can find out delta T by multiplying with the thickness. So this is known. So if you multiply by thickness, you will get the change in thickness. So one of the lateral strain is known, you will be able to find out the change in lateral dimensions in the other direction. Now Poisson's ratio is the ratio of lateral strain to the linear strain within the elastic limit. The ratio of lateral strain to the linear strain of a material when it is loaded within the elastic limit is known as Poisson's ratio. When a material is loaded within the elastic limit, the ratio of lateral strain to the linear strain, it is going to be a constant, and it is known as Poisson's ratio. It is denoted by nu or 1 by m. So 1 by m or nu is a representation, usual notation used for Poisson's ratio. So for circular cross section it is ED by E. ED is the strain in diameter divided by linear strain. So this is ED is delta D by D and E is delta L by L. For a rectangular cross section you can take strain in width. Lateral strain is strain in width divided by linear strain, that is delta L by L. It's also equal to strain in thickness divided by linear strain. So strain in thickness means delta T by T and E is delta L by L. So if you know the Poisson's ratio and linear strain, you can find out the lateral strain. So lateral strain is Poisson's ratio into linear strain. So Poisson's ratio gives indication of how much the lateral dimension is changing. Higher the Poisson's ratio, that means there is a large change in the lateral dimension, or lateral strain is more. Low value of Poisson's ratio means lateral strain is will be considerably less due to axial forces. So it is producing least effect on the lateral dimension when it is loaded. Let us work out an example. A bar of circular cross section with 50 mm diameter is 1.2 meter long and it is subjected to an axial pull of 40 kN. If the bar elongates by 0.08 mm and the diameter decreases by 0.001 mm due to this axial pull, find the Poisson's ratio and Young's modulus of the material. So the diameter of the bar is given as 50 mm and the length is 1.2 meter or 1200 mm, and it is subjected to an axial pull, that is tensile load 40 kN. So the force is 40 kN or 40,000 Newton converted into Newton. And if the bar elongates by 0.08 mm, so that means the elongation in the bar, that is in the 1200 mm, it increases by 0.08 mm. So elongation in the length is delta L 0.08 mm and the diameter decreases. This is a lateral dimension. Okay, diameter decreases by 0.001 mm. So delta D is 0.001 mm. Diameter is 50 mm. Okay, delta D is 0.001 mm. Now you can find out the linear strain, elongation produced divided by initial length. So 0.08 divided by 1200, you will get the linear strain as 6.667 into 10 raised to minus 5. Lateral strain is lateral dimension is diameter. So here delta D by D and change in diameter is 0.001. So it is decrease, but we are only considering the magnitude. So 0.001 divided by 50 is equal to 2 into 10 raised to minus 5. Poisson's ratio is mu is equal to lateral strain by linear strain. If you are taking the sign convention, you have to use minus lateral strain by linear strain. Poisson's ratio you should define as minus of lateral strain by linear strain, because when linear strain is positive, lateral strain is going to be negative. So to get always a positive value for Poisson's ratio, you have to use minus sign here. So that is only when you use a sign convention. When you are working with the numerical values, you can always define Poisson's ratio as lateral strain by linear strain. Sign is not required. So it is ED by E, this 2 into 10 raised to minus 5 divided by lateral strain we have calculated 2 into 10 raised to minus 5. Linear strain also we have calculated 6.667 into 10 raised to minus 5. You get 0.299. Now stress is P by A, load divided by cross section area which is resisting that load. So pi by 4 into 50 is the diameter, load is also 40,000 Newton. So you get the stress as 20.371 Newton per mm square. Young's modulus you can calculate as stress divided by linear strain. You have to take the strain in the direction of the load. You cannot take the lateral strain here. So it is strain in the direction of the load or linear strain here. So stress divided by strain will give the Young's modulus, because stress is Newton per mm square and strain has no unit, you get Newton per mm square. You can convert into gigapascal by dividing by 10 raised to 3. So it is 305.35 gigapascal is the Young's modulus of the material. That's all for today. Thank you for watching.